Microphone. Hey.
Koto. Welcome to this week's ICEperts webinar presented by the Antarctic Science Platform. I'm Megan Nicol from Antarctica, New Zealand. I'm your host for the day. I encourage you to ask questions using the Q&A function at the bottom of your screens. That's the one with the two little speech bubbles if you haven't done it before. And you can also upvote existing questions. So if you like it, then upvote it and it'll head to the top of the list. I'll raise your questions at the end with the panelists after their presentation. Today's webinar, The Warming of the South Pole, is presented by Professor James Renwick and Dr Kyle Clem. So thank you so much for joining us all the way from Wellington. Is it windy there today?
Absolutely not.
Oh,
sunny, typical Wellington weather.
It's windy here in Christchurch, so maybe you just sent it down this way, but I'll let you take it over from here. Thank you very much for joining us.
Well, thanks very much, Megan. And kia ora tātou. Hello to everyone who's listening in. So, this presentation is about a recent paper that was published on warming trend at the South Pole. And it's a really interesting combination of anthropogenic effects and natural variability. Kyle actually is the one who did almost all the work. I did get my name on the paper, but yeah, that's more from good luck than good management or effort. So I just wanted to start off by saying a number of people have published on this, but climate variability, natural variability is an incredibly big deal over Antarctica and the Southern Oceans. You know, it's a very dynamic environment. So seeing human effects, anthropogenic signals is pretty hard. So this has been a really interesting bit of detective work, pulling things apart for this paper. I think the only trend that's really been tied to human activity over the Antarctic is the southern annular mode, the ozone hole, causing the westerlies to speed up and contract towards the pole a little bit. Other than that, there's a lot else happening, a lot of tropical forcing and so on. So right now I'm going to hand over to Kyle, who'll really go through the presentation, and then we can hopefully both take a few questions at the end. So over to you, Kyle.
Thanks, James. And yeah, maybe counterintuitively, the anthropogenic signal in the SAM played a role in the warming of the South Pole, which is surprising because it actually was cooling the South Pole during the 20th century, which we'll discuss now. Share.
And then,
oh, here we go.
Okay.
All right. Yep. Kia ora. Thanks, James. Yeah, so as James mentioned, this work was published about a month ago in Nature Climate Change. And I'd like to start with just a map of Antarctica to really drive home a point of how undersampled it is. And so Antarctica is massive. It's about 14 million square kilometers. So that's about 52 times the size of New Zealand. And shown here are where we have weather stations measuring temperature with records that are longer than 30 years, which can give us an idea of what the climate is like. And you'll notice that most of these stations are located along the coast. So we have 5 right along the peninsula where the climate is a bit milder. And the rest are primarily located along the coast because it's easier to access them. Across this vast Antarctic plateau in the interior, we really only have 2 stations with temperature records that are longer than 30 years. The Amundsen-Scott station, which is located at the South Pole, and the Russian Vostok station, which they look maybe close together in this map, but they're over 1,200 kilometers apart. And outside of that, we really don't know what's going on across the plateau. Now, the plateau is really an extreme area. I would say it's the most extreme place on Earth. It's the coldest, it's the driest, the windiest, and the highest. So temperatures get down close to minus 90 degrees Celsius. The air is too cold to really get precipitation. Any water vapor in the air freezes and literally comes out as crystals. Winds coming off of this cold area, they drain from the very cold, dense plateau down to the surface, and These can reach speeds of over 320 kilometers an hour. And it's the highest region on Earth with an average elevation of about 3,000 meters, with a peak elevation of over 4,000 meters. And this ice sheet, which is sitting on land, holds over 50 meters of potential global sea level rise. And so this is a very important part of the global climate system, and also an important piece of the puzzle for understanding future global sea level rise. So to try and fill in the gaps, scientists use temperature reconstructions. And so they use those stations that we saw on the map, and they use shorter stations with shorter temperature records that are located in between. And they try to find relationships between those and try to kind of fill in the pieces of what temperatures might be doing in between. And so what we've seen over much of the 20th century up to about 2012 are very strong temperature trends, so very strong warming. And this is mostly located over West Antarctica and the Antarctic Peninsula. But there's a lot of seasonal variability as well. So the seasons are shown on the right 4 panels. And across the actual plateau, there's really not much going on. And so while global temperatures were increasing over this period, it looked like the plateau might be immune to this warming. And so this is why I was intrigued when I was looking at station temperatures during the year 2018. And I noticed that the 2 stations on the plateau, the South Pole Station and Vostok, they both had their warmest year on record in 2018. And shown on the top left is the time series of the monthly temperature anomalies from their climatological average. And there were times where temperatures at the South Pole here in purple were over 6 and even 7 degrees Celsius above their average. And the remaining 3 panels here are the anomalous surface pressure and temperatures. The pressure is contoured and the temperatures are shaded. And so for the year, we saw an anomalous high pressure over the plateau. And this was coupled with a broad and quite deep area of low pressure across the South Pacific. And this tapped into warm oceanic air from the South Atlantic and transported it inland up to the plateau to our 2 stations, the South Pole Station and Vostok, with the warming even reaching down across the Ross Ice Shelf and the Ross Sea. So really this cross-continental transport of warm, moist air from the South Atlantic. And looking at the 2 periods where we saw the strongest warming in May and June, we see a very similar pattern with a high over the plateau and a broad area of low pressure across the South Pacific, really marked in the Wet LC, so east of the Antarctic Peninsula. And this coupled pattern taps into this mild oceanic air and transports it up onto the plateau. And so this was really interesting because we don't really understand what brings warming to this remote region. So to place this year of 2018 in a longer term context, we looked at temperatures going all the way back to the start of the record in 1957. And on the bottom here shows running 30-year trends. And so the starting point here is the temperature trend at the South Pole from 1957 to 1986. And then that's moving all the way to the last point here of 1989 to 2018, so a recent 30-year period. And I guess what's interesting, we really don't know what's going on in the plateau, as I mentioned, and during much of the mid-20th century, or during the late 20th century, we did see cooling, which was significant. But after the 20th century, we saw 4 record warm years at the South Pole. So we saw the warmest year on record in 2002, and this was later surpassed in 2019, and then again in 2013, and the warmest year on record in 2018. And this is reflected with a quick flip of the cooling that we saw in the 20th century, turning to a warming trend, and then the strongest warming trend on record over the past 30 years of 0.6 degrees Celsius per decade, or a warming of about 1.8 degrees Celsius in 30 years, which is 3 times faster than the global average, which we were really impressed by, given the fact that it looked like this region might be immune to the global increase in temperatures. So to try and understand this, what might be causing it, we have 2 processes going on. We have an anthropogenic component, which heats the Earth through an increase in downward long-wave radiation. but we also have natural variability taking place on this. And so shown on the left are trends in the 500 hectopascal geopotential heights, or you can think of it as surface pressure like we saw in the previous maps. And the contour here shows the 10% significant level, so where the trends in the pressure are significant at 90%. And what we saw over 1989 to 2018 was a broad decrease in pressure across the South Pacific and into the Weddell Sea, and an increase in northerly winds to the South Pole. And so what we saw in 2018 looks to be consistent what we saw to what we've been seeing over the past 30 years. And looking at all possible trends ending in 2018, the strongest warming occurred from 1997 to 2018. And we see basically an amplified pattern of what we've seen over the past 30 years, with a very, very deep low over the Antarctic Peninsula and the Weddell Sea, bringing in this warm oceanic air from the South Atlantic and transporting it up to the plateau. And on the right are two wind roses. And so these just show basically the percentage of occurrence of wind direction. And so this is taken from all 6 hourly wind observations from the South Pole, so 91,000 of them. And that's shown on the top right here of where the winds predominantly come from at the South Pole. And you'll notice most of the time they come from the northeast or the east, so off the cold plateau. And then on the bottom right is the wind direction during really extreme warm occasions at the South Pole, where temperatures exceed -20 degrees Celsius. And so when we have warm events at the South Pole, the winds come more from the Greenwich Meridian or due north, and even northwest from the Weddell Sea. And so this recent pattern looks to be consistent with what causes warming at the South Pole. Now, the temperature record at the South Pole, as I mentioned, begins in 1957. So that only gives us a little over 60 years of data. And so it's hard to know if this recent warming is really unusual. And so to try and figure out how unusual it is, we have to use climate models, which give us a larger sample size. And these are free-running climate models that simulate, they're fully coupled, they're simulating the climate of the Earth, and some are with human-released greenhouse gases, and some are just free-flowing without human greenhouse gases. And so we call these the pre-industrial runs, and the historical, we have time-varying greenhouse gases that match what humans have done. And so shown here is the distribution of all possible 30-year temperature trends from the models with and without human-induced greenhouse gases. And the blue circles show the observed 1.8 degrees of warming. And so the recent warming, there was only a 0.1% chance, if we compare it to all possible 30-year trends in the climate models, there's only a 0.1% chance of this occurring under natural variability alone. And so that means it's incredibly rare, and there was very likely a human component, but it's not impossible to occur without humans. And on the right side here, this shows the highest 30-year temperature trend for each individual model. So there were 250 of them. And the observed warming lies in the upper 10% of the highest warming trend in each individual model as well. So again, very rare, but this warming can occur under natural variability. And so what we learned from this is that humans very likely played a role, but natural variability in this area is very, very extreme. And so it's very difficult to precisely determine what the role of humans played in this role, or in this warming. And on the right, we tried to understand maybe the mechanisms for what's causing this increase in storminess in the Weddell Sea and this circulation pattern. And so we looked at trends in the climate models, which are these box plots here, during the 30-year period of their strongest warming. And we look at large-scale climate patterns like El Nino and the southern annular mode, and a natural multi-decadal sea surface temperature pattern in the tropical Pacific, and also the pressure trend in the Weddell Sea. And so the models suggest that strong warming at the South Pole is mostly caused by a negative trend, or associated with a negative trend in the southern annular mode. and El Nino conditions, so positive sea surface temperature trend in the central tropical Pacific. And the IPO models are kind of split. About half had a positive trend, half had a negative, and so no big influence there. And the blue circle is the observed trends that we saw over the past 30 years. And so contrary to what the models say would cause warming at the South Pole, we actually saw a positive trend in the southern annular mode and a strong negative trend in the IPO. And so this is very unusual to get these two trends according to the models. And on the far right in orange, this is the distribution of pressure trends in the wet LC. So we've seen a negative pressure trend, our blue dot here, and the models have a huge range. Mostly they have positive pressure trends, which is opposite to what we actually saw in the past 30 years. And this is associated with this negative SAM trend that we'll look at later. But 20 of the 52 models that we used in this analysis did have a negative pressure trend in the wet LC, suggesting this could be an important mechanism over a longer term period of driving warming at the South Pole. And quickly, one of the ways that we examine what humans are doing to temperatures is we look at the mean of models that have observed time-varying greenhouse gases. And so shown here in the black line are running 30-year trends like we saw previously, with all the natural variability, the SAM and El Nino smoothed out. And this is supposed to reflect what humans, the actual anthropogenic signal from greenhouse gases. And these include volcanic eruptions. So this is from 1850 up to 2018. And so humans in the background, on top of natural variability, have been warming the South Pole. And this has increased with time. But in red here is the observed trends at the South Pole. And so while the climate models suggest humans have caused about a degree of warming over the past 30 years, the variability, the actual observed variability ranges from 1 degree of cooling to almost 2 degrees of warming. So it's 3 times larger than the anthropogenic signal. And so this tells us that humans are playing a role, but multi-decadal temperature variability is really extreme. And so next we look at the spatial patterns of sea surface temperatures and circulation associated with these strongest warming trends in the models. And so according to the models, strong warming is associated with warming across the western and central tropical Pacific. So more of an El Nino-like pattern. And it's associated with positive pressure trends across much of Antarctica and the South Pacific, consistent with the negative SAM trend. However, due to the large distribution or the large variability in the models in the wet LC, we see a local minimum in pressure trends in this area. And this results in an anticyclonic curvature that taps into this warm air from the South Atlantic and transfers it to the pole. And so the models inform us that this mechanism of delivering warm air from the South Atlantic is a robust mechanism. Sorry, we'll move on. And so next, to kind of tailor it more to what we've actually seen over the past 30 years, we just examined the 20 models that had a negative pressure trend in the wet LC or an increase in cyclones. And these are associated with warming across the central and western tropical Pacific and a wave train across the South Pacific that results in a lowering of pressure and increase in cyclones in the wet LC. And this is what transports our warm air to the South Pole. And so the models inform us that the recent warming is very likely tied to forcing from the tropics, or this warming that generates a wave train across the whole southern hemisphere. If we look at the observed sea surface temperatures, the trends over the past 30 years, we've seen warming, which is consistent with what the models say happens if you have a lowering of pressure in the wet LC. We've seen an increase in deep convection and precipitation as well. And so to test if this was a mechanism, we applied a heating anomaly in the western tropical Pacific where we've seen warming. And indeed, this generates a wave train across the southern hemisphere that results in a low pressure in the wet LC, transporting warm air into the continental interior. And this pattern down here on the bottom is consistent with our negative trend in the IPO. And And so this warming, this is very likely associated with natural processes that warm the Western tropical Pacific. But we can't forget that we also saw a positive trend in the SAM, while the models say should be a negative trend if the South Pole is warming. And that's shown in blue here, the time series of the SAM index from 1957 to 2018. And it's been a very steady increase over this whole period. And the IPO is shown in orange here. And one thing that's interesting is that the IPO is predominantly positive during the 20th century, and it flipped negative in the 21st century when we saw the record warm events at the South Pole. And so during the 21st century, we saw a total of 13 years where positive SAM occurred with negative IPO. So it's possible that this coupling could be playing a major role. And on the right side shows the South Pole temperature on the y-axis relative to the SAM index. And so this helps us understand what the SAM may do to the South Pole. And so we would expect the positive SAM to cool the South Pole. And indeed, this black line says that as the SAM gets more positive, temperatures at the South Pole get colder. But both the coldest and the warmest temperatures at the South Pole occur with a positive SAM. And the blue dots show us where positive SAM was with a negative IPO, and the orange dots where positive SAM was with all other IPOs. And so when a positive SAM occurs with a negative IPO, temperatures at the South Pole are about 1 degree warmer. And so this coupling is very likely important. And so I'm running over time. I'll quickly finish up here. So to understand how this coupling works, we drew maps where positive SAM occurred with negative IPO versus positive IPO. And when the positive SAM occurs with negative IPO, we see lower pressure across the wet LC. And the difference between these two maps shows that it increases cyclonic activity on the peninsula and in the wet LC and transports this warm air into the interior. And so what we've seen is a combination of natural variability. So the cyclonic activity in the wet LC is principally driven by the tropics, but when it's coupled with the positive SAM, which does have an anthropogenic component, we get intensified cyclonic activity in the wet LC, which helps to warm this. And so both natural variability and anthropogenic warming have been working in tandem during the 21st century, which is what's given rise to such an extreme warming trend that's more than 3 times faster than the rest of the world. However, large swings, really extreme swings, some of the most extreme in the world, occur in this area. And so it's one of the last places left on the planet where we can't really distinguish precisely what the anthropogenic role is. So I'll stop there.
Cool. Thanks very much, Kyle.
I'll take questions if there's any. We'll take questions.
Hello.
Can you see me?
Yes.
Oh, good. That's good. I can't see myself, which is probably not a bad thing. Thank you so much for that, James and Kyle. It was amazing. Actually, really good to see. I'm a communicator, not a scientist, and I understood that. So thank you, Kyle. Great to see. What's that? Sorry?
Kyle's pretty good at this kind of thing.
Pretty good. Yeah, pretty good. So it was excellent. So really good to see another scientist that has great comm skills as well. So that's it. That's just a wee pat on the back for you there, Kyle. So thank you very much for that. We'll head over to some questions now. So hopefully you are happy to answer these. And I guess the first one is how will, obviously this has been around, a lot of the focus has been around the Weddell Sea and South Pole, but is there any indication of how this sort of affects any trends in the Ross Sea region, which I guess most of us are used to working in?
Yeah, so as we saw in 2018, when this coupled pattern with an anticyclone over the plateau and a broad low pressure anomaly across the South Pacific, when this occurs, it transports warm air all the way across the continent. And so in 2018, we saw record high temperatures at, I think, Marble Point, located on the Ross Sea, the automated weather station there. And this was linked to the warm air coming in from the South Atlantic. And as it descends the transantarctics, it's going to warm up further, but that's where it originated. And so it's quite remarkable to have that connection all the way across on the other side of the continent.
It is indeed, and I guess most of us know the figures around if all of Antarctica melts, the sea levels will rise at least by 60 metres. But how is this process affecting the globe? You've told us how the around the heating of temperature and the process in turn sort of affect the weather or around the rest of the globe. Or does it?
Well, I don't know that it does directly. I think the effect of Antarctica on the globe, or on the southern hemisphere at least, is in terms of the broad north-south temperature gradient and the sea level component. And while this is, I guess, this recent trend is kind of concerning, we're going to have to wait quite a while before it really has much of an effect, because there's just so much ice on Antarctica that you've got to work hard to change the overall temperatures and melt enough ice to raise sea levels significantly. And maybe that last part's not quite right. Even 10 centimetres is pretty significant, but 60 metres is going to take an awfully long time.
Yeah. And one thing that I'll add is that we have to trace this back to the source in the Weddell Sea, where temperatures get warmer and warmer and warmer. And so we're bringing this warm air originally from the Weddell Sea. It's above freezing. And when it first makes contact with the continent, that's where we're closer to that 0 degrees Celsius line. And so while temperatures have not gotten above freezing at the South Pole, if we trace that back closer to the coast, this is where melting might occur, and in time it might move further inland.
Yeah.
Another question here. What is noticeable that the variability so strongly increased in the last 20 years? I'm guessing, what is it about the last 20 years that has caused that?
It's a really good question. So the variance at the South Pole tripled, if I remember right. It's been quite a while since I looked at that map. But yeah, the variability increased very, very significantly after the 1990s. And it didn't increase anywhere else on the continent. And so we couldn't really trace it back to a specific reason. So it's a localized process. So we looked at the 20 other stations around Antarctica, and none of them showed an increase in variance like the South Pole did. And so it's a really good question, and I don't have the answer.
More research needed.
Next question is, as I understand your commentary, you're saying the IPO is entirely naturally driven. Are there anthropogenic or climate change influences on the IPO?
So if you have warming in the Western Tropical Pacific associated with the natural process of the negative phase of the IPO, this warming can be intensified as it works in tandem with increased greenhouse gases. And so the warming that we've seen over the past 30 years associated with the negative phase of the IPO is likely stronger due to humans and increased greenhouse gases, but it's still the gradient that's important, because you need to generate the deep convection to send that signal down. And so if all of the tropical Pacific is warming, even if that warming trend is higher, if all the tropical Pacific has a higher warming trend, then the gradient doesn't change. And so you don't necessarily get more deep convection to send that signal down.
And we can be pretty sure that human-induced warming is affecting the IPO and affecting the El Nino La Nina cycle, but exactly how is still an open question. There's 100 theories and 100 different answers, and we just don't know yet.
I don't think we fully understand the IPO.
Yeah. Well, I don't.
Yeah, I don't.
Ozone and positive SAM are related, I understand. How might the trends you see play out with decreasing atmospheric ozone?
Right.
What was that?
So as the ozone hole recovers, is that what you're saying?
How might the trends you see play out with the decreasing atmospheric ozone?
Right. So we've had this positive trend in the SAM the last 50 years or so, and that's mostly been driven by ozone depletion, the ozone hole. But partly there's been an effect of greenhouse gases as well. As the ozone hole recovers, that would drive a negative trend in the SAM in the other direction. So the westerlies moving away from the Antarctic coast. But there's still the positive influence of greenhouse gases. So and instead of the two working together as they have done in the last few decades, they're going to oppose each other in the future. And again, there's no clear-cut answer to that. If we see strong emissions reductions, then the negative trend from the ozone recovery should dominate. But if we don't, then we may see not much trend at all for the next 40 or 50 years. It's yet another fairly open question, I would say. Yeah. But I guess a bit like Antarctica itself, the variability in the SAM from one month to the next is pretty strong. So that the trend is going to be subtle, I would say, the next 50 years, and probably overwhelmed by just the natural ups and downs.
And finally, and thank you for all the questions, everyone, but finally, have you looked at the impact of volcanoes and methane escape, etc.?
No.
That was an easy answer, wasn't it?
Yeah.
Okay, well,
yeah, no, there's quite a lot you could talk about there, but yeah, in terms of this study and what's happening at the South Pole, I guess the answer actually is no.
Okay, well, look, thank you very much, James and Kyle. I found it fascinating. I'm sure everyone else online did as well. That is all we have time for today, unfortunately. But thanks so much for sharing your knowledge with us. It's much appreciated. I'd like to say to everyone else, join us the same time, same place next week as we dive into scuba science. I didn't write that bad dad joke, somebody else did. Professor Ian Hawes. We'll update the platform webpage shortly. That's this afternoon, so tune in there if you want more details. So James and Kyle, once again, thank you very much.
Okay, thank you. Cheers.
Enjoy your day if you're in Wellington. Lovely.